about sudden quenches in strongly correlated lattice systems. And so what I mean by this is that one prepares a state in some initial state. And I will just call it psi I. And then what you do is to change the parameter in your system, and you watch what the state does under the new parameters and how the evolution looks like. I think this is one of the most simplest setups you can think of for dynamics in a system. So you just change something and you then look afterwards what is happening. And so what I will talk about is here that one does a global parameter change. So I don't do a local excitation, but really a global one, which means that I put in an extensive amount of energy into the system. So let me put here globe. So what you can think of, for example, in these ultra-cold atoms, is if you confine them to an optical lattice potential, you suddenly switch the height of this optical lattice potential. Or like we have seen it in Eric Conant's lecture, you suddenly switch the interaction in this system to another value and look how it evolves. And so questions which are very important in this connection is, for example, if you do this whole thing, if you have a quantum phase transition. So let me say my parameter, let me call it G, has a quantum phase transition. And you have, for example, long-range order over here. Whereas you have a gap system here. You know that the correlations behave very differently. In this regime, typically the correlations decay exponentially with a distance, whereas on this side you decay towards a constant of the correct correlation. And so if you now do a sudden quench across this phase transition, I mean, what you are interested in, for example, is how do the correlations behave? Do you have that the correlations will restore some kind of long-range order or some reminiscence of this phase? So let me say here, it is formation or destruction of correlations. Let me say more generally, sometimes these systems have very particular dynamics at short times. So you are interested, what is this particular dynamics? And you will see one of the basic examples or earliest examples in these systems. Then, I mean, if you now assume that the first evolution has passed and you look at your system. So one of the questions is, does my system reach at some point a steady state? And if so, can we characterize it somehow by a thermal ensemble, or what can we say about this state? And so all this is a very, very lively area at the moment, and it has started with the realization of these cold atomic systems, because these cold atomic systems are very well decoupled from the environment, so that on a relatively short time scale you can really say, I'm now looking at this sudden quench in an isolated system. certainly at longer times or close to Feshbach resonances, there might be dissipative effects like atom losses or things which one needs to take into account. But I mean, first of all, we will just look at the times which are almost isolated in these systems. And so all these questions have now been studied really a lot, and so I'm not going to cite all the people working on it. It's an enormous amount of publications which came out in the last few years. And so, in particular, these questions on the steady state and thermal state are studied a lot in the, or you are looking at different systems which have an infinite amount of conserved quantities which are non-trivial, so-called integrable systems, or you can do it in non-integrable systems which have only trivial conservation laws, and therefore you expect them more to thermalize at some point in these systems. And so, I mean, there's a lot of research going on in this direction. I would like to first focus on this first point, so the short time dynamics, and tell you a little bit about the formation of correlations in these systems after a sudden quench, and do this in particular in an optical lattice system. But before I get more concrete, let me just, I mean, somehow this setup is very, very simple. We have our initial state, and then we have our Hamiltonian under which we look at the time evolution. Let me call it HF. And so what you can do is, well, typically you cannot do it, but in principle you could do it, is to determine the eigenstates of this Hamiltonian. So let me call them n, with the energies En in this system. And if you know all this information, you know the time evolution of the system. You know that your state can be decomposed, so your initial state can be decomposed onto these different eigenbases, and I will call this just Cn. And so you can say that now I decompose my initial state, and so what I'm left with is these eigenstates. I know the time evolution of my eigenstates. It's just with the eigenenergies. And so you have written down the evolution of the system. But I mean, typically in many body systems, it's pretty hard to get either of these in the whole spectrum. So this makes the complication in this treatment. But let me look at this a little bit more carefully. So what you see is that certainly you have always a pure state if you have an isolated system. So what I call here thermalization cannot be something which is on the whole system. The mic is somehow, is it too close or?
It's fine.
It's fine? Okay. So I mean, you still have a pure system, so it cannot be the whole system which has thermalized in this sense. So you need to find a different definition of what you mean with thermal in these systems. And so let us just look at observables. And the time evolution of observables, I just take the simplest case of just one observable which is depending on time. And so you can expand it in the same way, only that you now have your state on this side and on this side. So you need 2 or 3 indices. So you sandwich your operator, and you have the time evolution, which is now the difference n times t. Okay, this does not help yet very much, but I mean what you can further see is that if you assume that you have no degeneracy in your system, there are 2 different contributions. One of them is the contribution where these states are equal and you will have no time evolution. and the contribution where these states are non-equal, and since we assume non-degenerate ones, you will have a time oscillating time evolution in this system. So let me just write this down. So here you have just the non-evolving term. And then you have the term like above with n which is not equal to n. Okay, and from this you see already that if you are interested in the long time limit, you could assume that if the frequency don't have a certain structure, you just say they are averaging out and you are left with this so-called diagonal ensemble of the system. And you can deal in the long time limit, you can try to study this ensemble. But at the moment, what I would like to do is to go back and take an operator which is now a correlation function at different distances and look what kind of evolution does this term, which is a pure dephasing term, cause for these kind of correlations. Do the correlations spread? Are they disturbed in another sense? So we will focus on this for the moment. And so the question, or the system we will look at, is an optical lattice. And so, as always, I'm biased to choose this since I know this best, since I worked on it. There are many other very interesting examples in the literature. I mean, there are really several hundreds of papers now on these kind of quenches in cold atoms. And so, let's take an optical lattice. So, yesterday we learned that we can form, the first lecture we learned that we can form an optical or periodic potential for the atoms by just using two counter-propagating light fields which form a standing light field. And so let's assume this kind of potential for the atoms. So now we can have our atoms moving in this kind of potential. So we will have a so-called tunneling term if the atoms move from one well to the other. So let me write down the many-body Hamiltonian directly. So we have a tunneling, which is mainly on neighboring sites. So I remove a particle from site I plus 1 and put it on site I. And certainly the inverse. And depending on the definition with a minus sign. And then if two particles meet on the same site, we had a very short-range interaction of the van der Waals potential, which has a range which is much smaller than a lattice site. So what we get now for an interaction is only if the atoms meet on one of these sites. And so we take here an on-site interaction term, which is just given by the density operator. So I have nj atoms on a site and they interact with the remaining atoms on the site. So this is the interaction term. So we have done quite a bit of approximations to get to this Hamiltonian. I will not detail them here because I don't have the time. But I mean, you can happily read them somewhere. So it's called tight binding approximation. And I will have something in my notes on this if you want to know more about this. Okay, so many of you know about this Rosa-Hubbard Hamiltonian, as I asked last time. But let me, nevertheless, for the few of you who haven't seen it, just talk a little bit about the quantum phases. So you have now two terms which are competing here. So one term which is this kinetic term, which is delocalizing the atoms. So here you would just get free bosons or which are or BC, which is delocalized. And you have this interaction term where you have to pay an energy if two atoms meet on the same lattice site. So you can see if you have just one atom here, this gives 0. But if you put two atoms, you get an interaction energy, which is U. So this is a penalty which you have to pay. And so what happens now is that you get a quantum phase transition. In this model, if you look at the ratio of this parameter, u over j, at a critical value. And so on this side you have a superfluid, and on the other side what happens is the bosons really don't want to see each other, and if you have commensurate filling, what they do is to localize in each lattice well. So you get a state which is a so-called not insulating state, which if I just depict the atomic limit, which means for j equals 0, I'm getting a little bit close, it's just the same mean number of atoms on the same lattice side. And so this is for commensurate filling. Okay, so now let us see a little bit. So in the superfluid, this phase has no gap. So if you want to do an excitation, you can just make a slightly move one of, or deform one of the wave functions, and you will have the normal Oberlubov excitations at low energy. So a spectrum which starts linearly at low energy. Whereas in the mod insulator, you see if you want to create an excitation, the thing you can do is to move one particle from one side to the next side, but then this costs you an energy u. So you have a gap which is of the order of u, at least for large interactions. And you know you have to do these particle hole excitations, which are the excitations in the system. Okay, so I will mainly now deal with this kind of system in a one-dimensional setup. And so there it's a little bit special. So this phase transition there is the Kosterlitz-Thouless phase transition, and you go to a critical region, which is called typically as well the superfluid region, which has algebraically decaying correlations. So no real long-range order, but algebraic decaying correlations. Okay, and so the first experiments in called atoms in optical lattices, which have really realized a cubic lattice, have seen this kind of transition in 3D, going from a very light lattice, where you don't have a very deep lattice, to something which is very, very deep, where you localize the atoms. And so they have monitored this transition by monitoring the momentum pattern in the system. Yes?
Sorry, could you just say a word about what you mean by commensurate filling and why it matters?
Okay, commensurate filling, what I mean is that you have an even, if you count the wells, let me say you have a number L, that you have the atom number which is an integer, an integer times this length. So, n is equal to L times some integer number. Why do I need this? Because if I look at a sketch...
So I'm sorry, you mean density is 1 over integer.
Sorry?
You mean density, the fractional filling is 1 over an integer. That's what you mean?
You have an integer number on the lattice side.
Oh, okay.
You have either one atom on each side,
so a half-filled lattice doesn't count.
Half-filled, I mean, in bosonic case, does not count. Because if you're away from this filling, so I mean, this is the fact, I mean, this is this mod insulator if you localize. You have really atoms in the single sites. But if you now remove, let's say, just one of these atoms, you don't know where to put this hole, and it delocalizes. And so you have directly in transition, you don't form this gap anymore.
Excuse me.
Yes?
I have a question about this transition.
Yes?
So I think it's not clear what the chemical potential is, but is this transition the same for all different chemical potentials?
Okay, so then I will not reduce the introduction too much. So let me write now this phase diagram. What I have drawn here is to keep the number of atoms fixed. So one can as well have a look in the, as a function of the chemical potential. And so let us do it here. And take here the chemical potential. And so what you get there is now, so, wait, large U, no, J over U. So this is the weakly interacting, this is the strongly interacting case. And what you get there is typically this kind of mod lobes, it's called. This is one. So, let me explain a little bit. So if you are in the weakly interacting limit, you have just a superfluid region. So this here is all superfluid. And it doesn't matter at which density you are. So you can continuously change this chemical potential, and you just increase the density. Since it's not commensurate, it doesn't matter. So you just increase it monotonously. Whereas, if you now go inside this region, you know this phase transition only takes place if at commensurate filling. So these lobes, which I plot here, is really at n equal 1. So a mean filling of n equal 1. Here it's the mean filling of n equal 2. And so only in this case you get these mod insulating lobes. And so the line I have drawn here is the line of density 1, which bends a little bit down and goes further in this system. And so equal density lines would now behave like this if they are not commensurate. So you go somehow into this point, okay, it's not nicely drawn, but you go deep inside here, you stay superfluid up to the really case where you have no hopping anymore. And so this is something one can at least easily understand. If one just takes the limit of j equals 0, you can just try to calculate these kind of points, and you will see that if you plot the density as a function of the chemical potential, you will get these kind of steps which go up. So this you get just by taking this term plus a chemical potential term. So you add the term which is the minus mu sum over j and j, and you minimize the energy. So this you can do as an easy exercise, and you will find this line, you will find these densities.
So
Yes?
is the transition the same all along this curve?
No,
So it's closer to tallest.
only in the tip. So this point here is a multi-critical point, which is very special. And in 1D, it's here, so one calls it, this transition one calls the commensurate incommensurate transition. So you go from something which is incommensurate to something which is commensurate. And here this transition point is very special. You are at the commensurate filling, you are, so to say, at fixed filling, and you go through here, and in 1D, this is a Kosterlitz-Dawes transition. And so in higher D, you have as well different critical exponents here and here. Okay, so just, yeah, this was more or less all I wanted to say on the transition. Yes?
Why is it easier to have superfluidity, so I have n bar equals a big number. I mean, it seems like it's
Yes.
it's sufficient to have a smaller j
Yes.
in my n bar.
So let's have a look at a simple picture. I take again, let me take now 2 atoms on each side. So what happens if I do this excitation? So I need to evaluate this interaction energy. So what I had initially, so let me say the interaction energy initial, if I have the 2 everywhere, it's just 2 times 1 is u, and I have 2 sides. So I just take these 2 sides. So this is 2u. And if I do this particle hole excitation, that I hop 1 over here, I don't have any interaction energy here, but here I have now 3. So I have 3 times 2, so I have 3u. So you see the difference here is still u. So the difference has not changed. It doesn't depend on the filling. The first gap is always u in this case. But what about the hopping? So if I have this hopping, what I will get is, if I apply this operator here, okay, it's now the other way around, v dagger I plus 1 bi. So there I know I will get a factor. So this I apply on the state, which is n bar. And so what I will get is, here I will get n bar minus 1. Here I will get n bar plus 1. But I will get the bosonic enhancement factor. And so this will be the square root of n times n plus 1. And so you see, whereas the difference in the interaction energy is independent of the number of particles, you get that here you gain an energy by delocalizing the atoms, which is enhanced by the bosonic enhancement factor.
So it basically means that I can hop any one of those.
You can hop much, exactly. Easily said, it's you can either hop this one or you can hop this one to the other side, so you have a factor 2, roughly speaking. And so this means that it's much easier to have up here the superfluid than the Morton slate. Okay, so let me just give you as well the value for this critical value. So this can be calculated in mean field, for example, or numerically. So these are bosons, so numerical methods are very strong here. You can do quantum Monte Carlo in higher dimensions and get very accurate values. But just to give you an idea, it's about 5.8 times the coordination number of the lattice, so the number of nearest neighbors of the lattice at filling n, which is equal to 1. Certainly in 1D this is not a very good approximation, and in 1B you get a value which is about 3.8 from numerics. And so this was done by Kühner and Munin, this reference. But it's in the notes. Okay, so this transition has now been observed in these optical lattices. What they did is to load a bosonic cloud into these optical lattices relatively slowly, so that they reach almost the ground state of the system. And then what they do is to let this cloud fly apart and look at absorption pictures. So you release both the optical lattice and the trap, the cloud expands, and so what you measure is approximately the momentum profile before you switch off the potentials. And so what you now expect is that in the superfluid you have coherence over a long range. So what will happen is that these different, somehow, it's like scattering at Young's double slit. If you have something coherent which is scattered at the double slit, you will see an interference pattern. Whereas if you do it from something which is incoherent, light sources in the double slit, you get a very broad background. And so this is exactly what they saw. And I will just misuse some plots which are not the static ones to show you what I mean by this. So for example, the superfluid is this picture over here where you see these very strong interference peaks, whereas the mod insulator is something over there where you see really this very broad distribution. And so you have the coherence, so what this probes is the coherence of the superfluid in the system. Okay, so now I would like to start with one of the initial experiments which is already here, but let me switch it off for a second.
So,
Yes?
just to understand this page you were showing. Okay, sorry. So those spikes are the
These are the interference
components
peaks.
of the.
So typically if you have a young double slit experiment, which is very similar, so you have just a double slit, you have light which is coming coherently, what you see on your screen is an interference pattern which has some very sharp peaks of the intensity of the laser light. And so what you do now here is not to let this kind of coherent laser light shine on it, but you have a coherent meta wave which is diffracting on this lattice. So it's very similar to this situation, and this was why you get these very sharp peaks in this system. Okay, it seems not.
No, I mean, was that momentum axis in the two?
So, I mean,
Just sort of the block, the wave function of sort of the block state of the superfluid, right? The different peaks of different.
the different peaks, so here you have the first interference peak, and then you have the next interference peak. So here you can think of Kx and Ky, for example. And so what this means in the lattice language is then, I mean, this is the Brion zone. So you have the different peaks, or one interference peak which repeats at the different Brion zones. Okay, one of the first experiments which had been done on the dynamics in these systems was then to load the system inside this optical lattice. So if this is the lattice strain, what you do is to slowly load it into the lattice with time, then hold it for some time, and then so that you create, for example, a superfluid state, and then you suddenly increase it up to a value which would be in the mod insulating state if it would be statically. And so let me write here mod if equilibrium. And then they looked for different times here. So this is now the evolution time. What happened in the system? And so the first guess was somehow, I mean, here you have a coherent system, and now you ramp to an interaction strength where the equilibrium situation is incoherent. And so what they expected was that somehow the coherence would die out in the system. And so let me show you the figures. So it's again the same figure I showed before. And so now, what you see here is different times. So this is this different waiting time over here. So this time is now increased from one plot to the next and going further there. And so what you see is that first of all you have this superfluid, then it's vanishing, but then it comes back after a certain time. So you have oscillations and you restore the coherence in your system after a certain time. And so this certainly makes people a little bit curious. I mean, that you have coherence which goes away and then comes back has been seen before, but I mean, it's still always surprising. Yes?
So is this figure once this potential applied and there's no change on the system, and these oscillations are observed even though there's nothing else?
So these pictures are here at different times.
Okay, okay.
Yes?
And so at each different time you remove the lattice and make a time of flight in the
Yes.
engine to get the momentum,
Yes.
and then you recreate the system,
Yes?
do the same thing, so it's
Yes?
so extremely tedious or extremely very.
Yeah, it's quite tedious for them. I mean, they want to optimize the procedure to create the cold cloud. Yes. And so, I mean, each of these pictures is again an average over many, many observations. Yes?
So can you remind me what was changing in the previous picture compared to this one? Because
So the previous picture, I just used the same picture. I was lazy. So because the equilibrium picture looks really the same, you don't see the difference. So if you're in equilibrium at a low interaction strength, you see picture A. If you're in equilibrium at a large interaction strength, you see picture B. And so if you change the interaction strength, and you always, so what they do there is to switch, to make the switch to a different height, so that they go almost adiabatically into the lattice, almost equilibrium. Then they see as well these kind of different patterns depending on the final height of the lattice. But I assure you, you will not see the difference. Okay. So let me give you an easy explanation of this. I mean, the experimentalists knew this themselves. So just to give you one example where you see something particular if you do this kind of question. And so now what we assume is that they ramp up the lattice really to a high value, and so that the Hamiltonian can be considered as mainly being this interaction part. Just try to write down the evolution Y-line for yourself to see why, if you just take the interaction part, you get these oscillations. So we now use this representation which we had before. So we say the wave function, the evolution of the wave function is now given, okay, by the application of the Hamiltonian certainly onto my initial state. And now I said I will just take the U term into account. So the U term is diagonal in the Fock basis. So what I can do is to expand this state into the Fock basis. So I will have here an initial state which can be written over different ensembles of n. So I have here my n1, n2, and so on. And I have some coefficient which depends on this distribution. So what happens now if I apply this operator onto such a state? On each of these states, what I get is, I get an integer here and an integer here. If I get an even integer here, I get an odd integer there, and the other way around. So in total, this is an even integer, which I can divide by 2, and it's still an even number. So what you see is that this is an integer number. So it's an integer number. nevertheless to which of these states you apply it. And so what this means now is you have an integer, you have e to the minus I u t times some integer. Let me call it f for the moment. But this means now that you can find a period. You know that if this is 2 pi times another integer, you will revive or you will have the same phase again. And so now this number can certainly change from state to state. But let us have a look at the period t, which is defined by this. So this is now the 2 pi some integer over u times the m. And so now what we know is that m is somehow 1 or bigger, or will be mainly contributing if it's bigger than 1. Okay, so what this means is if I get something bigger here, this means I get a smaller time. So the latest time after which it revives, and each of these integer revives, is the time where I set this to 1 and this to 1. And so this is the period after which each of the Fock states is reviving in this system if you don't have any hopping in it. And this is the time you operate, which is the identity at a certain time. And so this is why you have, again, the coherence which revives in these systems. And so this is called as well the revival in collapse, the experiment of the wave function. And so let me note, I mean, this is certainly only Q because you have here an equally spacing of the energy levels so that you have the same frequency distance between the eigenstates, which makes them revive. So it's like a harmonic oscillator in some sense.
Excuse me?
Yes?
So from my understanding, so as you evolve along this picture, at some parts interaction dominates because it's so-called localized. In other parts, hopping dominates. Is this correct?
No. I mean, yes and no. So in the Hamiltonian, you have only the interaction. So you don't have the kinetic energy anymore. But you still have the delocalization of the initial state. So this gives you the coherence in the system. But I mean, the energy is only given by the final Hamiltonian, and there we have assumed that we are in a really, really high lattice where you don't have any hopping anymore.
I mean, how do I have superfluid if I don't have
You don't have superfluid. This I didn't say.
Oh, so these are not superfluid phases.
The initial state is a superfluid state, which has a lot of coherence. And so now you take this state and you time evolve it with the Hamiltonian, and you will see that, okay, in the meantime, if the time is not this time, you get some different frequency for different numbers of n. So somehow these kind of, before the coherence that you had in your state will turn away, you will get a different phase for each of them, but then they will come back at this time. They meet again. And so here you have again your original superfluid state. And only in between you have a dephasing of the different contributions of these different Fock states, and then you meet again, because you have the same phase after some time. So it's hard to talk somehow, I mean, you have the delocalization, you have the coherence in the system, but it's not due to the Hamiltonian, so you have not the kinetic energy in the system. Yes?
Right, so I guess the crucial thing is that this interaction piece only has infinitely conserved quantities, right? Because each nj is a conserved quantity if you only have the interaction, so it has to be some type of periodic system. But
Exactly.
then there will be some sort of thermalization given by the residual small hopping, right? So
Yes. So what I have told you up to now was just taking this part into account. This is certainly an integrable Hamiltonian. You can solve it exactly, and you have an infinite number of conserved quantities, which is exactly these Fock states. So I mean, this is why we have this very strange behavior. And so now if you switch on a little bit of hopping, you certainly will get something which does not revive fully, but where if you plot this coherence peak versus time, so just this maximum of the peak, you get something which first comes back but becomes smaller and smaller. And so in the experiment you had as well seen this. In the experiment it was just a dephasing which came from the inhomogeneous distribution of the density, but you can as well get it if you correct the integrability by switching on the J, then you get as well a dephasing of the state. But I think it's still not totally clarified. I mean, we did quite a bit of work on what is this steady state, what is its characteristics. Okay, so much for this quench, and I'm not sure if Anatoly will discuss it tomorrow as well in his formalism, so then you have seen it already. So now I would like to go a little bit away of this. I mean, this was a very, very simple case where I had no hopping at all and just put the interaction energy. And so now I would do the contrary, and I will switch on somehow a little bit of the kinetic term as well. But I will now not start in the superfluid, but I start in the mod insulator and go down a little bit and look at the evolution of the correlations in this system. And so why do I do this? Because it's theoretically much more easy to describe than in the superfluid. And so therefore, I would like to show you how one can treat this. And you will see that what we find as the evolution is much more general. And this is why I take this example to explain you what has been found in many models by now for this evolution of the correlations. So somehow the situation I consider now is to start here at really a high interaction state, and I quench my system down to a smaller value of the interaction strength. And so what you would somehow naively expect, that somehow the coherence should restore at least to a certain extent. Let me call it atomic mod insulator. And so I would like to introduce one technique which can be used in this regime of high interaction strength quite well for static properties or other properties. And so this is a quasi-particle approach. Since one sees very nicely the physical interpretation in this kind of approach. And so what we do now is to say, okay, we start in this mod insulator, which was given, it's really the atomic mod insulator where I have an N filling on each of the lattice sides. And so what I know is that as long as I stay in the mod insulator regime, the particle fluctuations are typically quite weak. And so what we say now is that we take the local basis, which is typically for bosonic atoms going from 0 occupation to the maximal number of occupation. We reduce it drastically, and we take now only the states with the filling N. So this is now a local basis on a side J. What we do now is to say, okay, we take now this basis N, and we take plus minus 1 into account. So we have only 3 local states which we take into account. So this is a drastic simplification and typically works quite well if you're somewhere above this regime. What you can now do is to introduce auxiliary operators to describe this kind of, or to describe the action of the normal bosonic operator on this system. And so the aim is it to find auxiliary operators in which your Hamiltonian becomes quadratic, so that you get rid of this interaction term in the Hamiltonian. And so let me call them A. And so now I introduce two different ones, the plus and the minus. And so the plus ones take our average occupation and they rise to n plus 1. So they create an excess particle. And the minus ones, they lower the particle number by 1. So this is just kind of a definition. I define my creation operator that they do this onto the local state. Then I can take somehow my basis and look how my original operator can be represented in these new operators. And so what we need now to look is how does the original operator act on such a state. And so we can take the three different states we have. And so this operator always creates a particle. We can represent the particle from to n plus 1 is represented by this one. We need enhancement factor into account, so we get here n bar plus 1. So this would correctly describe the term where I apply it onto this operator n. So now we need as well to apply it onto the operator n minus 1. So this operator applied to n minus 1 gives nothing. And so what we will see is that one needs, now we need to destroy a minus operator, which is somehow the whole. We need to destroy the whole to get the average filling n here. And so here we have the square root of n, which is the bosonic enhancement factor. And so if one does this, you can check that on all the three states you get the correct action of the operators. Further, these A's are bosonic operators. So they fulfill the bosonic commutation relations. I'm not going to do the calculation. But one has an additional constraint. Since, if you have created an excess particle, you cannot create another excess particle. It doesn't make sense to somehow create twice an excess particle. So what you want is that if you apply this operator twice, that this gives 0. And the same for the minus 1. You cannot create two holes on the same side. This would, this does not make sense physically. And so analogically, the annihilation operator can as well not act twice on the same side. Then additionally to this one, you certainly have as well the case where you have the excess particle acting, or the excess operator, and the whole operator. But I mean, it doesn't make sense as well to have a whole and an excess particle on the same side. So what we need to constrain as well is that if we have now, if we are counting the number of excess particles on a side and the number of holes on the side, that this is 0. So we can have either an excess particle or a hole on the side. And I mean, this kind of transformation is done since a long time, let's say. And I mean, it was used quite a bit, for example, by Ehud Altman and Hassan Auerbach for the first time to as well calculate something time-driven in these cold atomic systems. And I mean, there's very nice papers by Sebastian Huber and Gianni Platter, who use this kind of bosonic quasi-particles. So they are as well very good in equilibrium to obtain results, and very much used there. But I mean, during the quench, which I have described you, we started to apply these operators, and we noticed that, sadly, what we see is that the occupation here, if you cannot enforce this exactly, grows up in your face, and this approach somehow, if you cannot enforce these constraints exactly, blows up. And so what we did is to use another approach, which is now to introduce another auxiliary particle, which is now a fermionic one. So why do we do this? For fermions, this would be fulfilled directly. So we don't have to impose this from outside, but for fermions, this is easily fulfilled. Whereas this one is still not fulfilled. So this will be the one which is remaining, and which we need to see how to treat it in the problem. So let me mention, so this approach works very well as well in 2D and 3D, so this bosonic one. But how we go now to the fermionic ones, we use a Jordan-Wigner transformation, which is more easily done in one dimension. So the remaining will be mainly for one-dimensional systems. So let us do a Jordan-Wigner transformation. To obtain fermionic quasi-particles. Okay, so this is just the usual. We introduce them by introducing a string operator, which is in 1D, one can easily introduce it. And the relation is now given by this, whereas the string just counts the number of atoms before the site j. So here sigma j is smaller than j prime, j prime smaller than j, sorry, and j prime of sigma. So I count the particles if I have my chain. I count the fermions, and this is my side j. I count all the fermions which sit before side j, and I put a minus sign corresponding to the number of fermions. So for the, one has as well to order the spin up and the spin down, and this is why the string for the plus and the minus are a little bit different. So now for the minus operator, term, which is more, which counts the number of plus fermions which is on the side. So this is just convention. Okay, so now we have these C's which are fermionic operators, but as I said before, what we want to obtain is a quadratic Hamiltonian. So let me discuss why we have now a quadratic Hamiltonian in these operators. So this Hamiltonian now, okay, I write here a term, a projector, which should fulfill somehow the remaining constraint which I have not yet fulfilled. So this is just standing there for the moment. And then let us see, what does the interaction now do? So the interaction, we said, is giving you an interaction energy. So it was before the term where you had u times u half times sum over n minus 1. So now you have only the three states, which are the n plus 1, and n minus 1. And so you now just need to count how many times you have the excess particle to find the interaction energy. So you get u half times the number of the excess particles. Because we start from the mod insulator, so we say if we have n bar, we get 0 interaction energy. So we shifted just the 0 of this interaction. And then what you get additionally is, okay, you gain energy if you have now the holes. So what you have to count as well is how many holes you have in your system. Further, you have the interaction, the kinetic energy. And so there it becomes a little bit more complicated. So you need now to consider different situations. So the first situation is where you hop a particle. So you have your mean value, you have an excess particle, and you hop this. So what this means is that you annihilate the excess particle on this side and you create it on this side. And you can do the same if you have a hole. So this is this first term. Then you can do the same with the hole. So you hop a hole from one side to the next. But this has not yet represented the process where you had a hole here and you hop one particle here. So we need as well to take this process into account. And so this will be given by, if you hop this over here, this means that you annihilate a hole and you annihilate an excess particle. So you have here both annihilations. Of plus and minus, and you can certainly do the counter process where you create the doublon and the hole out of something steady. So you have here as well the creation of this term plus Hermitian conjugate. Okay, but what you see now is that we really gained something. Since this Hamiltonian, if you neglect these projectors, the Hamiltonian is now quadratic in these new operators. So this you can solve.
Sorry, why they come in different signs? The third term of the, why they come in different signs?
It's due to the commutators. It's due to the introduction of the strings which we had. So one has to carefully write down. I mean, you want bosonic hopping. So in the fermionics, this can give you the sign in these systems. Okay, so what did we gain? It's a quadratic Hamiltonian. If we neglect the projector. And so this is what is typically done. You just neglect the projector and you solve this Hamiltonian and the time evolution. And so so this is as well what we now do. So I will not do the calculations here. I think you are all familiar to Bogoliubov transformation that you can diagonalize this Hamiltonian. So let me just write down. Neglect the projector means I put the projector to identity. And so then can be calculated by Bogoliubov transformation. And you find a Hamiltonian which is diagonal in the new Bogoliubov operators. So let me say Bogoliubov operators. I will now use gamma plus and gamma minus. And so I don't want to outline these steps. So what you do is to diagonalize a Hamiltonian, and then you can, for these operators, easily get the time evolution of the operators, and then re-express the time evolution of the state with these time-dependent operators. And so what you obtain is the full evolution of the wave function, but within the approximation which we have made. So the approximations were that we reduce to these three local states, and that we neglect this projector. Otherwise, everything is exact. So, and this time evolution is now given by a product over k, and you have some transformation coefficients which depend on k. And what is important, you have here, this is the dispersion relation of the Bogoliubov particles. Times t. So this gives you the time evolution. And we have here a term which creates you a Bogoliubov quasi-particle of this excess form, and it creates you a Bogoliubov particle of the whole form applied to your initial wave function. Okay, so what you see, first of all, there must be a minus sign. So what you see is that you create Bogoliubov quasi-particles which are counter-propagating. And you create always a plus and a minus at the same time, and they are counter-propagating. Then these quasi-particles evolve with a dispersion relation, and they propagate through the system. So let me just reduce this expression in the limit that we have a final Hamiltonian where the interaction is still quite big. Because then we can go to an even more simple picture, which is just these excess particles and holes. So what one finds is then that one can expand these coefficients, and one obtains that this time evolution state is the original atomic mod insulator. Then there's a state which is just a constant state, which is the correction to the final interaction, or the sine k. So you see this term is just constant, and then there's one term which is the important one, which has quite a similar form, but now you have here the time evolution of your function t over h bar of the operators ck plus c minus k minus applied on. And so what I did here is really just to go to the large interaction. I mean, this expression you can evaluate numerically, but just to see a little bit more clearly what happens, let us consider this large case. So you have your original state, you have a correction, and this is the correction to make, or to have an eigenstate again, so this is just a perturbation correction. And then you have the part which is evolving. And so what the quench did now is to create from the originally homogeneous state, it creates quasi-particles which have an excess particle and have somehow a hole. So you have your state. And what you do is now something like this, whereas this excess particle propagates with a certain momentum in one direction, and the hole propagates in the other direction. And so this propagation, how fast this propagation is given by the dispersion of the quasi-particles. So this we saw over here. And so this dispersion in the large interaction limit is just a cosine dispersion. So this is why I have the cosine over here. And so you see, but it is not that one really creates this in real space, but what we have is a coherent superposition of different functions of all these different pairs of neighboring sides. But you have as well the same you created on this side, over here, on the next side, and you have a coherent superposition of all of these creation of these quasi-particles. And these propagate. Each of them, in each of these superposition state, let me write it a little bit sketchy like this, you have the propagation of these particles, or this excess particle, and the holes in counter direction. And so this is something which is much more general, has been seen in other models beforehand, and this was why I wanted to show you at an easy example how one can somehow calculate this and see this. So let me give you some references, or first of all one reference, which is the reference of Calabrese and Cardi. So what they proposed is that you create, by a quench in a conformal field theory, you create this kind of antenna quasi-particles which then propagate semi-classically through the system. So it's a PRL 2006 type. And so since then there have been many models in which this has been seen by now. So I wanted to show you now that this is as well something which one can see in experiments. And so for this, let me show you these experiments over here. So these are in the group of Markus Greiner and Emanuel Bloch, two different experimental setups. But what is common to them is that they have a microscope, so this big lens over there, that they have a very, very good resolution of or resolution in space. So they really can monitor single lattice sites in this system. And so what they can see is typically what they do is to increase the optical lattice very rapidly to freeze the distribution in the system, and then shine in light and scatter many photons of each atom so that they can see single atoms in these sites. And so during this process, what happens is that if you have not only one atom in the sites, but two atoms, you lose the atoms. So typically, they scatter with a photon and the two atoms, so you lose them. So what you will see is only the parity distribution, which is locally resolved. So you will see if you have an even or odd number of atoms in these systems. But this is quite nice, because this parity distribution, if you do single shot measurements, you can as well extract the correlation function from it. And so they can get, for example, the even density correlation at over different distances. And this is exactly what we somehow need. If we have now created our quasi-particles, which in the large U limit correspond to these excess particles or holes, this means we have changed the parity by these quasi-particles. And so we will get, if this is the background density, and we have changed it here by 1, let's say created a hole and a doublon, these will give the same signal, and we will measure the correlation directly between these quasi-particles in the system. Certainly, if you go to lower U, you get some corrections to this picture, but just take this simple picture of these zeros and double occupied site, which you can now measure here. And so these are the results which they found by doing this measurement. And so, let me put so this is now this correlation of the parity versus time. And so it is measured for different distances. So the upper curve is the distance 1, distance 2 is below, and so on. So this is really the distance of the correlation. This is not the measurement of the density. The density stays constant in the system during this process. And so they took or loaded the atoms into this high optical lattice and suddenly switched down the optical lattice. And this is the result, what they see. So they see now this evolution. First of all, they see this kind of peak coming up here. And then they see that if you go to further distances, this peak comes up at a little bit later time and moves somehow through the correlations in the system. So you have somehow really these quasi-particles, or you can now really see in these correlations, these quasi-particles will spread through the system and get different distances, and therefore you see this peak which evolves through the system. And so, just to mention, so the points is the experimental results, the line is the quasi-particle approach, and we did as well numerical simulation for it, which is this green line, which certainly fits much better. But I mean, the quasi-particle approach at least gives you the rough structure, even if it cannot give the correct amplitude in this situation, because we are here already at a relatively low interaction strength.
Sorry.
Yes?
Sorry, what are the solid lines?
So the solid lines is DMG.
I mean for the lower part. D equals 2, 3, 4, 5, 6.
So it's the same coding. So this is the quasi-particle approach. The d over g and the points is the experimental results.
Oh, sorry.
And
What is?
so this red line is just a guide to the eye of the peak moving through the system.
What is d here? The small d.
The small d is the different distance of the correlation.
Oh, I thought it was dimension. Sorry.
This is here this distance of the correlation which you measure.
And what is the dimension? 3D or
This is in 1D.
1D? Okay.
So they created one-dimensional tubes and looked just in 1D how it's spreading. Yes, so this was, I mean, since I introduced the fermions, it was for one-dimensional systems. And I mean, these conformal field theory systems and the systems I mentioned, these are one-dimensional systems in which this kind of quasi-particle entanglement spreading has been seen. Okay. So just to show you that if we don't have this very low interaction strength, this is now again the comparison of the quasi-particle approach and the numerics. You see it works much better if we have a higher final interaction strength. So just to give you a little bit of confidence that with this approach one can really describe the system relatively well.
Excuse me?
Yes?
I'm a bit lost. So this was for fermions, right? This
No, the experiment is for bosons
boson.
in 1D. So only our quasi-particles are fermions.
So why do I have this type of eigenstates for bosons?
The
So-
fermionic ones?
I'm lost
Mhm.
here. So you started with fermionic Hamiltonian?
I started with a bosonic Hamiltonian.
Oh, okay.
I have a bosonic system, and now what I did was first to introduce bosonic quasi-particles or operators which are somehow representing the excess particle and the whole. But since I said that I cannot have two excess particles on one side, what I did is to include this constraint and artificially introduce fermionic operators.
So you introduced Jordan linear transformation
Exactly.
for this. So in some sense, I can think of fermions.
In this sense, you can think of fermions of the quasi-particles.
Okay, so these quasi-particles are strongly interacting.
Here in this system I have, I mean what you see is that you only create two of them which are counter-propagating, so they don't need, we don't need to care about the interaction.
I mean, if they don't interact, why do they have such a coherence? And I mean, at least you have to have a little bit of interaction to have that kind of. I am thinking naively about BCS. So
You have here, you have created the pairs. So this is your coherence, which
so-
you have created by the quench in the system.
And quench is strong interaction, which is repulsive.
So the original system is a strongly interacting mod insulator. And in this strongly interacting mod insulator, you find now a coherence evolution of these quasi-particles. So that's. And I just want to show you here some numerical results. Works. Come on. Okay, finally. So just to show you that, I mean, if we go now across the phase transition, there certainly our analytical approach breaks down, but we further can do our numerics, and we see a very similar picture. So sorry for this, it's now inverted. So this is distance 1, the lower one, and going up is the larger distances of the correlation function. And you see again a peak. So the different colors are different final interaction strength. And you again see a peak evolving through the system. And you see that for different final interaction strength, this evolution has a different velocity. But I mean, the form is not changing too much. It is just that you get some kind of tail if you go to weaker interactions. And so I have not much time left. So what I would have liked to show you as well is that one can really show analytically that this onset of the onset of the correlations is really before this peak comes, it's exponentially suppressed. So this we can show analytically. So in this region you have an exponential suppression of the correlation here before the peak arises. There's no change, or exponentially small change, and only afterwards you see a change. So you have a kind of light cone which propagates out in these systems. So I would like to summarize this in a plot. So I have here my distance, I have the time, and so now what I see is that at larger distance I have only something changing at larger time. So here I have exponentially small changes. Whereas in this regime I see this peak coming and big changes occurring. And so that you have this kind of maximal, or this velocity now here of this light cone is set by the maximal velocity from the quasi-particle dispersion relation. So if you have your quasi-particle dispersion relation, omega versus k, typically something like a cosine, let's say, what you have is that the velocity is defined by the derivative with respect to k. So it's the slope of the dispersion relation. And so if you have a bounded dispersion, what you see is that there exists a maximal velocity somewhere in this dispersion relation. So let me call it here, it's this slope over here. And so this light cone, or there is a maximal velocity which is set by this maximal velocity of the quasi-particles, outside of which only exponentially small changes occur, and only after this something happens in the system. And so this was, or is, a very general theory has been found or proven mathematically for spin systems. And it's called the Lieb-Robinson bound. And this is a really, really important theorem from which many different things have been proven. And so I recommend this paper to you if you're interested. It's quite old already, but I mean there has been many work which is based on this proof of this Lieb-Robinson bound in the systems. And let me just mention some names. Quasi, for example, proved then this form which I have shown here for the equal time correlations, that there's a maximal bound. I mean, Hastings has proven the exponentially clustering theorem, that if you have a gap in the system, you have exponentially decaying correlation. So, I mean, it's really a very important theorem in these systems. In these bosonic systems, it has not been proven, and counterexamples have been seen. But I mean, here we see that if you stay at this low energy sector, everything is behaving like one expects from this system. So to conclude, let me just make some comments on what I wanted to say on the thermalization. So what you see is that, first of all, you have these short time dynamics where the light cone is spreading out. And so if you want to look for a steady state of thermalization, you can only look somewhere here. And so you will have always for, or in this short-range interacting Hamiltonians, you will always have this kind of evolution outwards, at least in these systems, in the spin systems or for which it's proven. And you can only expect something which is steady or thermal at these distances setting in later on. And so sadly, I didn't have now the time to talk a little bit about this thermalization, but I mean, if you are interested, just ask me after the lecture. And so, thanks for being so brave to still be here for this last afternoon lecture. And I would like to conclude.
Quick announcement, the picnic is this evening at 6 o'clock. So because people are leaving already. Follow me inside because it was raining. Basically, I heard the main part of the story.
Yeah, I was
I actually didn't know that this is, so I read in my mouth.
No, I actually thought that like no, then I can tell you
Der war richtig, so